Well, I really appreciate you guys getting up and being here at this hour on the fourth day of this great but very busy school. So maybe I'll just ask if there are lingering questions from last time. Are we not using this, or? Yes. That is actually in the way that I was phrasing it. If you're above 2 dimensions, it works for any theory. Yeah, we will discuss 2 dimensions today. There are definitely contributions from farther away. The area law that so the term area law has multiple meanings. It's actually not a great, I mean, physicists love to use the term, but then they use it in 6 different ways. And so I actually prefer to avoid it. But the statement that there is a divergence, a UV divergence proportional to the area of the entangling surface is true above 2 dimensions, regardless of whether the theory is gapped or gapless. That does not exclude the presence of long-distance correlations and entanglement and so on. So I was just referring to the divergence associated with the entangling surface.
But the statement that that's the leading contribution to the entanglement.
Well, leading in, if I fix everything and take the cutoff to 0, that will always be the leading contribution, regardless of the theory. Yeah. Yeah, so we're gonna talk about that. Yeah. Okay, so let's just do that now, actually, just to clear the air, so I don't leave mysterious statements about except in 2 dimensions hanging around. So the way that we got that area divergence from a Rindler viewpoint was simply by integrating an entropy density over space close to the entangling surface. So it looked like this, and I have my region A, and we just did an integral over space. But I should, as I mentioned, this can be computed in multiple ways. There's a replica trick. I mean, another way to do it is by doing a mode decomposition if you have a free field theory. And then again, you have to impose a cutoff. And what happens is basically, I mean, the nature of the entanglement in that picture for a free field theory, and you just look at modes, is that any given mode in a free theory will be in its ground state in the vacuum. And the ground state obviously entangles, the ground state in the wave function entangles this part with this part because a given mode has support on both sides. And then you just add up the contributions to those modes, from those modes, and you get infinity, so you have to cut it off at some wavelength, and that's your cutoff. And so in a free field theory, you get the same result just from a mode decomposition. Okay, so but anyway, what we found was that, so zooming into the entangling surface, S of A had a contribution, which was an integral, which was the area of the entangling surface times an integral over the coordinate perpendicular to the entangling surface of the entropy density, okay? And this thing was, went like T to the D, where D is the number of spatial dimensions. And this in turn went like 1 over x1 to the D. So let me just say D Okay, and that's where I got this area of dA over epsilon to the d minus 1, where epsilon is just going to be my lower cutoff for this integral. And you can see that this is not true, so this thing, except in d equals 1, where now, instead of a power law, I get a log. Okay, so in d equals 1, you get something which is instead, so you instead get something which is S of A is like log of 1 over epsilon. Okay, so now we get a logarithmic divergence instead. And in fact, we can be more precise. Well, let me say it this way. When you have one difference between a logarithmic and a power law divergence in quantum field theory is that usually for a power law divergence, the coefficient is not very meaningful, meaning that if I change my regulator, the coefficient of that power law will change. This is not, I shouldn't say it's not meaningful, that's not true. The correct statement is simply that it's scheme dependent. It's meaningful in the sense that once you fix a scheme, it's a meaningful number and you can use it to extract physics for sure. But it is scheme dependent and sort of, depends very sensitively on details of how you implement your scheme, whereas the coefficient of a log divergence is not like that. The coefficient of a log divergence in quantum field theory is robust. If I change my definition of epsilon or how I implement some particular cutoff, the coefficient of the log will not change. And that makes it worth making a little bit more effort to, so I really didn't try to get this coefficient. One could work harder and be very precise about the scheme and so on and get the coefficient here. But here, we should be able to get the coefficient without so much work, and it's sort of a little bit more, it carries a little bit more direct information. So, and in fact, you can get that very easily if you believe this formula. So I'm not going to do an honest calculation. So an honest calculation of this, one way to do it is by the replica trick. And there you're dealing with a two-dimensional field theory, and you can go ahead and actually get the coefficient without a problem that way. But I want to get it more from the physical intuition that this picture gives you, where you're just seeing the fields heat up as you get close to the entangling surface. Okay, and so so to do that, we just have to be a little more precise here. Well, first of all, we don't have an area anymore; it's just a point. Okay, maybe if or at least for each. So now dA. So in d equals 1, dA is some set of points. Okay, so there'll be a coefficient which is the number of points. So if I have 6 intervals, they'll have 12 endpoints. So that'll be 12. So there'll be some number there. Instead of area of dA, I would, let's call it number of dA. Okay, so I'm going to have that for sure. Now, here, I can actually be, well, in both of these steps, I can be more precise. So remember that we're just, when we get very close to this point, the fields are getting very hot. And so the entropy density that you're talking about that's going to give you the leading contribution is the entropy density of the UV fixed point of your field theory. So I'm going to assume that I have a field theory that has a UV fixed point. And then the leading contribution will be from the very high temperature limit, which will reflect the physics of my UV fixed point. Okay, so I'm going to assume, I should have done this whole thing over there. Okay, that's okay. Let me just do it here. Okay, assume a UV fixed point. And that thing is going to be a CFT. It's going to have some central charge. Okay, and it turns out that in two-dimensional CFT, the entropy density is just proportional to the central charge. So that means that for T large, so when you're accessing the UV fixed point, the entropy density, there's just a formula for it, which is C over 6 2 pi T. C, yeah. This is my UV fixed point. Okay, so this you get by some CFT tricks, just a fact about, so you already knew that when you have a CFT in 2 dimensions, it has to be proportional to the temperature. There's no other scale, so, you might have guessed that it's going to be proportional to the central charge, just by the fact that if you take the tensor product of 2 CFTs, the entropy density will add, and then you do some torus partition function calculation to get out the coefficient. Okay? Meantime, what was the temperature? The temperature was 1 over 2 pi x1. And so when you put these things together, you get C over 6 for each endpoint log 1 over epsilon, as far as the dependence on the cutoff is concerned. Okay? Again, you can reproduce this by an honest calculation, for example, using the replica trick. Okay, well, so now we see something interesting comes out because of the fact that we have a log divergence. I need something else with units of length to go with my 1 over epsilon. So I really shouldn't be taking the log of 1 over epsilon. Okay, and that's simply because, from this point of view, that's because I was doing an integral of 1 over x, and that integral actually has a IR divergence. Okay, so if I really just had one endpoint, and that's all I had, then I would actually get, even with the UV cutoff, I would still get a divergence from the infrared. Okay, and that's because if in a CFT, so if I'm actually in a CFT, and then I have this formula, and when I do this integral of 1 over x1, I get a divergence not only from short distances, but also from long distances, and that's because I have long range entanglement. Okay, so we need some kind of, so to get finite answer, so you need some kind of you need to fix your infrared. Okay, and so, I mean, one way to do that is to just consider an interval, okay, in which case you can guess that what's going to go here is simply the length of the interval, okay? Another way to do it is if you have a gap theory, then when you do the integral of the temperature, see, then this thing will only be true for high temperatures, and at lower temperatures, it'll zero out. Because the gap theory at temperatures below 1 over the mass has no degrees of freedom, has no entropy density. Okay? So one way is to say, okay, so if I have a CFT, but I have a finite interval, of length L, then you get C over 6. So then the number here is 2. So you'd get C over 3 log L over epsilon. So that's just purely from dimensional analysis. Okay? Wait, let me just finish my sentence. Yeah. Here I've just put C because I have a CFT, so I don't have to specify CUV. And there's finite stuff. And the finite stuff, just to be clear, is going to depend on the details of your scheme. And you can see that from the fact that if I change my definition of epsilon, then so I have some epsilon prime that's equal to 2 epsilon or something. When I write this in terms of epsilon prime, I get some c over 3 log 2. So the finite piece has to be there to absorb changes in my scheme. Okay? Yes, go ahead. Yeah.
So can this be done with certainty without any, can you actually get this form, or you just are using some other methods that you're not?
Right, so yeah.
Because it could have been t squared also, as far as I can tell.
What could have been t squared? This?
Yeah, instead of 3.
No, it couldn't have been t squared because that has the wrong units. So the entropy density is always like t to the d if you're if you are at a fixed point. So you have no other scales. There's no if there's a scale in the theory, like a mass of a particle, then of course it's much more complicated. Okay.
So in some units, it's 3
Yeah.
said alpha, c, and what else?
I mean, yeah, I don't know, like there's Boltzmann's constant and stuff, but anyway, there's some, by this squiggle, I mean that this is the dependence on t. But there'll be, of course, some coefficient here, which will depend on the theory. Yeah. So but in this case, this is an actual equal sign. This is a actual precise formula for the entropy density of a CFT in 2 dimensions. Okay? Okay. Yeah. I don't actually know how to use dimreg to calculate an entanglement entropy. Oh, I see. No, but I mean, dimreg keeps logs. So I see what you're saying. If you just put a d plus epsilon here or 1 plus epsilon, no, I think you would keep the. I'm not going to attempt to do that in front of a large crowd of people, but I mean, dimreg. The good thing about it is it keeps logs. So I suspect it would still work. Interesting. Okay, let's talk about it later. I've never thought about doing the calculation that way. I was going to say here that if you don't believe this derivation of this result, you can do it honestly by the replica trick. And what you're doing is you're calculating the partition function on alpha copies of the plane that are that have a cut, and now my cut is just an interval, and this thing topologically is a sphere. Okay, so it's an n-sheeted Riemann surface, which is topologically a sphere, and the partition function can be computed by some CFT tricks, and then by the time you're done processing everything, you get back to this thing. Okay, and the finite thing here is going to be scheme dependent. And in any given scheme, you can compute it, and it's meaningful, but it's going to be scheme dependent. Okay, so that's one example. The other example I mentioned is if we have a massive theory. Okay, and here you would expect S of A. So a massive theory, and let's say the full half line. So actually Rindler, if you want. Okay, so if I have a massive theory, then the theory comes with a natural IR cutoff. So I don't have to just do a single interval. I can really do the entire half-line, knowing that past some point, the amount of entanglement is going to die off. Okay, and the way you would see that, so if it's massive, then you have basically S of t is CUV over 6 times 2 pi t for t much greater than the mass, and 0 for t much less than the mass, and it interpolates in some way. And by the time you're done doing the integral, you get c over 6 log 1 over the mass times epsilon. C over 6 because I only have one endpoint. And this is now, I'll call it CUV. Okay? Okay, so what I'm going to do, is what I've already started to do, is just run through a bunch of examples, focusing for the rest of today's lecture on 2 dimensions. And the reason is that, not that 2 dimensions is the only interesting place to compute entanglement entropies, but it's relatively simple, and all of the relevant physics kind of comes to the surface easily. And you can, write down formulas for everything. And already we're starting to see that the entanglement entropy is telling us something about the physics here. So if you have, just as an example, if you have some spin chain, and you believe that there's a second order phase transition, and you think you know how to tune the parameters to the critical point, a good way numerically to test that hypothesis is to compute entanglement entropies. Okay, and if you see that the entanglement entropy is indeed logarithmic in the length of the interval, then that tells you that you have a CFT. And furthermore, from the coefficient, you can extract the central charge of that CFT. Okay, from a numerical viewpoint, this is one of the easiest ways to figure out what the central charge of some fixed point is that you've reached by doing some spin chain or something like that. Okay? Okay, so the obvious next step is to do a massive theory, but on an interval, okay? And of course here it will, so there's a difference in the CFT case. Often you can just write down the answer by doing a, by doing a calculation, by using CFT techniques. Basically, the replica trick, it comes down to computing the partition function on some particular manifold, and we have powerful CFT techniques for doing that. If it's a massive theory, then you don't have those CFT techniques, and so it's going to be much harder. Okay, and so explicit results are much harder to come by for massive theories than for CFTs. Okay? Yes?
Now, it was kind of important for you to get the coefficient correct, so I just wanted to ask for some intuition. I mean, I think it's very believable. You find a central charge. Can you give some intuition for the 1 over 6? Like, is there some physical reason why we find this coefficient in this place?
I think I'm going to fail at that task, but I mean, I can tell you that the number 12 is littered throughout CFT formulas, and that comes from, in some sense, it comes from the Casimir energy of a scalar on a circle. So it's just there are like 12s and 6s all over the place in CFT.
One should think of this as
Well, that's from one way of looking at it. I mean, there's some way of doing the CFT calculation that reduces to, after a long, a whole bunch of conformal transformations that relates it to the Casimir energy on a circle, via some modular transformations and so on. That was just one example of how this number 12 like falls in your lap. There may be better answers to this question. Yeah. Okay, so let's do, I mean, the obvious next thing would be a massive theory on an interval. Oh, one thing I was going to do, let's just set this up here. So we're going to be doing intervals, and so here we had, the first example we had was a log. So this is CFT is a log. Something maybe I should mention is that, of course, this formula only, you should never take a formula like this and apply it unless L is much larger than epsilon. So you might be worried that, oh, it's going to become negative if L is smaller than epsilon. Obviously, this is meaningless unless L is much larger than epsilon, and then it's always positive. Okay, a massive theory on an interval, of course, that's actually pretty hard to compute in practice. So it's actually only been, it hasn't been computed analytically, actually, in any theory except a massive fermion, free fermion. Even for, you might think, okay, a massive scalar, free scalar, surely for that I can just do this calculation. But even for that, you sort of have to resort to numerics, amazingly. So these things are actually not that easy to compute. But we can just sort of guess what it should look like. And basically, we can take inspiration from this, or from the idea that if my interval is finite, then we wouldn't expect much entanglement past the correlation length. So if this is 1 over m, and this is 1 over m, you would expect these to be kind of the only contributions to the entanglement entropy. Okay, so 1 over m is the correlation length, or the Compton length. And now, on the other hand, if the interval is small compared to 1 over m, then it starts to look like you're in a CFT. Okay, and so you would expect something like this. Okay, but if the interval is large compared to 1 over m, then it should simply become constant. Okay, so we expect to be again this for L much less than 1 over m, and for L much greater than 1 over m, plus finite pieces, okay? So you expect something which turns over, starts out like this, and then just saturates. So this is, okay, at some, yeah. Okay? And this is, when you do the calculation for a free fermion, this is what it looks like. Well, okay, so far we've been talking about the vacuum. So everything here was in the vacuum of the theory. Oh wait, let me do actually one more thing in the vacuum. Sorry, so a CFT, we can complicate things a little bit by putting the CFT on a circle, okay? So let's say a circle of radius r. There, we can expect something interesting because, okay, so I have some interval of length L, okay? So is the entanglement entropy going to be sensitive to the fact that I'm now living on a circle? Well, if the length is very small compared to the radius of the circle, then probably not, okay? But once it starts getting comparable, then indeed it should be, and in a way, what you can think of this circle as being an infrared cutoff on the complement. Okay, so here, even when I had one interval, the complement was infinitely large. So I had cut off my infrared divergence because when we're talking about entanglement between this and its complement, if A is of finite length, I don't get an IR divergence. But there's still this infinite complement. So here I can cut off the infinite complement by putting it on a circle. And then we know that you're going to be sensitive to the fact that you're on a circle, because if we take the other limit, where L is almost the whole circle, we know that the entropy in a pure state, like the vacuum of a region, is equal to the entropy of its complement. So S of A, and that thing will be C/3 log the length of the complement, okay? So we have S of A equals S of A complement implies that basically S of L in an abusive notation equals S of 2 pi R minus L, okay? And that is almost enough to just guess what the answer is. So that together with the fact that you know when L is very small, it looks like this, okay? And you might guess that some trig function is going to enter. And if you have really good intuition, you might guess that the trig function is going to enter inside the log. So, so you get C/3 log of sine L over pi R times the coefficient, which is pi R over epsilon. Okay, so this, again, this is from an honest calculation using the replica trick. And the point is that it obeys this condition, because if I replace L by 2 pi R minus L, then I have sine of, sorry, this is, then I have sine of pi minus L over 2R, and sine of pi minus X is equal to sine of X. Okay, so on here, we see that it goes up and then comes down again. So for small L compared to R, so if I have my R over here, say 2 pi R over here, well, okay, so it's going to go up the same way, and then it's going to come down, okay? So this is for CFT on a circle. And so now we get an interesting phenomenon, which we haven't seen in any of these so far, which this is the first time we've seen the entropy decrease as we increase the size of our system. So that means that if you're in this regime, as you add to your system, the entropy goes down. And we already discussed 2 lectures ago that if the entropy goes down when you add on to your system, you must have entanglement. So of course, we know we have entanglement in general because we're in a pure state. So any entropy we compute is an entanglement entropy. But what I'm saying now is that I'm saying something more now, which is that if you're in this regime, where L is more than half the size, okay, so of course we know, so this is A complement. Of course we know that this is entangled with this because we're in a pure state. But now I'm saying that if I add on a little bit, so if I make a little delta A. The entropy goes down when I include this bit, okay? And that means that this bit is entangled with this. It's no surprise. I mean, you know, so what I'm saying is that if I trace out this part, so now I just have this interval and this little bit, that thing is, of course, in a mixed state. And you could ask whether between this bit and this, there's entanglement or just classical correlation. Of course, we expect that there's entanglement. It would be quite weird if there was just classical correlation, but now we can prove it, okay? Because the entropy has gone down, therefore there must have been entanglement between this and this, okay? You couldn't prove it that way. Of course, it's still true, there are other things that you can compute in, there are other entanglement measures that you can compute in CFT, like this negativity and so on, that establish something about the entanglement. So there's always going to be entanglement. I mean, because at short distances, there's definitely entanglement, okay? Because yeah. The only theory for which it's been honestly calculated analytically, not numerically, is the free fermion. But this expression is going to be true for any massive theory. Yeah. Yeah. Okay, so here we have to, good, that's a good question. Just as this formula does not apply when L is smaller than epsilon. In particular, you might say, well, what if I have no interval at all? L is 0. I'm just going to plug L equals 0 into this. I get minus infinity. This is crazy. We know the entropy is 0. Okay, again, you cannot apply this unless L is much larger than epsilon. You cannot apply this unless L is much larger than epsilon, and 2 pi r minus L is also much larger than epsilon. So you cannot apply this formula. You can't just plug in L equals 2 pi r and expect to get something sensible. So that's a very good question. So there's sort of this regime where, you know, beyond which it doesn't apply. So here, this is, let's say, epsilon. Say that again? Yeah, yeah. Yeah. Yes, that's right. No, there's only one. Okay, so if L is much smaller than 2r, then you reduce to this case. Because the 2r's cancel. Similarly, if L minus 2r, 2 pi r is much less than epsilon, then again you reduce to that case for the complement. But if you naively plug in L equals 2 pi r in here, you get 0 for this, and then log of 0. Okay? Okay? Now, you might want to do something like a massive theory on a circle, et cetera, and you know, people have done things like that and so on, but to keep it simple, I just want to introduce one effect at a time, basically. So I have my interval. The simplest case is it's a CFT in the vacuum. Then one effect I just want to turn one dial at a time. One dial I can tune is to make it a massive theory. A separate dial would be to put it on a circle. A third dial would be, let's not be in the vacuum anymore. Let's be in an excited state. And there, what you get, of course, will depend on the excited state. But a very simple, nice, important excited state that we should all care about is the thermal state. Okay, so we're going to do a CFT on a line in a thermal state. Okay, and see what we get there. And that's interesting because now, for the first time, we're in a mixed state. So CFT on a line at temperature T. I don't think so, for a reason that I'll give you in a minute. After we do this example. So again, now what's the difference now in terms of the calculation? So again, you go back to this picture. I mean, I didn't mention it, but in this calculation, of course, now we're on a cylinder, but since we're still in the vacuum, the Euclidean time direction is infinite. And when you do the n-sheeted thing, you still get something that's topologically a sphere. In this case, we're on a line in terms of the space direction, but since I'm at finite temperature, my Euclidean time direction is now periodic. So actually the calculation is very similar because I'm on a cylinder, again, just the cylinder is this way instead of this way, okay? And so whereas this thing is still oriented horizontally, so it's not quite the same calculation, but it's basically related by an analytic continuation in L, essentially. It's like making L imaginary, okay? And so you can again guess what the answer is going to be. It's going to be the same as this, but with the sign replaced by a sinh, okay? So you get sinh pi TL. So the sign is replaced by sinh, and the R is replaced by 1 over 2 pi t, which is the periodicity of the, 1 over t is the periodicity of the Euclidean time circle. So you get epsilon. What does this formula look like as a function of L? And what's the physics going on here? So that was just, you do some calculation, you get an answer, but like, what does it mean? So of course, as always, for L much smaller than the thermal length, which is 1 over T, you get the same thing you always get, C over 3 log L over epsilon. But when L is large compared to 1 over T, then you get log sinh, which is going to give you a linear term, okay? And so you actually get, so for L much larger than 1 over T, S of A is, you still have this term, but now you get a term which comes from this, the log of this. I mean, there's a T here, which is going to give you C pi over 3 TL. What is this C pi over 3 TL? Well, we've already met this C over 3 pi TL because it's right here. Even I know that 2 pi over 6 is pi over 3. So this is the entropy density of the CFT at a temperature T. Okay? So this entanglement entropy is picking up a part which is indeed due to an entanglement near the entangling surface and a thermal part, which is not due to entanglement between the interval and its complement. Okay? So we get another curve which actually lies above the CFT one, the CFT in a vacuum. So now I have to be more careful. So this one is on the line in the vacuum. And now you always get the same beginning thing, but now you get a linear piece. So this is CFT at finite temperature. And you get this linear piece for large L. Okay, now, yes? A time-like interval? Right, so, okay, at least in sort of conventional thinking, entanglement entries are defined for spatial regions, but you can be bold, and Tadashi and friends have recently been talking about this kind of pseudo-entropy and time-like entropy and so on, where you allow your region to be time-like, and then indeed you can get formulas out by replacing L by IL. But in that case, of course, you do get an imaginary answer or a complex answer. Whereas here, I mean, even though I mentioned that you somehow get this by taking L to IL, in the end, by the time you're done doing everything correctly, you still get a real answer for my entanglement entropy. I didn't end up with log of I sinh or something like that. Whereas in this time-like entropy story, you get complex entropies. And the interpretation of those, I think, is still somewhat up in the air, but it's an interesting thing to compute. Yeah. Okay. Do you guys notice anything about these four curves that they have in common? One thing they have in common is they all look the same for small l. But is there something they have in common when I look at their behavior in general at arbitrary L that they have in common? They are all, I believe the term is concave, but yes, I'll give it to you. They all have negative second derivatives. Okay? And this is not, I think convex is like this. Yeah, normally I wouldn't say that with confidence, but I spend a lot of time thinking about convex functions, so I'm actually pretty sure about that one. So they're all concave, so they all have a negative second derivative, and that's not an accident. No matter what you compute if you're in a relativistic field theory, in a spatially uniform state, all of these states were spatially uniform. If you compute the entanglement entropy of an interval, you will find as a function of the length of the interval, it is a concave function. And there's a reason for that, and the reason is strong subadditivity. Okay? And so basically, if you apply strong subadditivity, which if you recall was this, to an interval, well, how would we apply this to an interval? Well, we're interested in what happens when we change the size of the interval. So one thing we can do is make A and C very small and B arbitrary length. So make A and C infinitesimal. Notice, by the way, you might say, oh, you're not allowed to consider intervals that are infinitesimal because that's smaller than the cutoff. Well, okay, we could say it's not smaller than the cutoff, but it doesn't matter actually because nowhere in this formula are we evaluating S of A or S of C. Okay, so I'm just evaluating S of AB, which is still large, S of BC, which is still large, B and ABC, those are all large. And I'm just taking differences. And this thing, if I just rearrange it a little bit, is just a second derivative. So this is basically, well, if I put these things on this side, it basically says that S, the second derivative as a function of L, is negative. Okay? And actually, historically, this was the motivation for this inequality to be conjectured, because the feeling was that an entropic quantity, of course, if you have independent systems, it's extensive. But let's say you have some interacting set of systems, the entropy should not grow more than linearly with the size of your system. Okay? And so that is the same as this inequality, and that's originally why it was conjectured. Okay? And this gets me back to Nima's question. So I don't think that it's possible to have a regulator that brings you to zero given these curves, because I think it would have to be convex somewhere. So I don't think if it really is a regulator that respects all the rules of quantum information and so on, you can attach a curve like this to 0, 0 if you want L equals 0 to be 0. You agree, Nima, or? Okay. All right. Yeah, interesting. Okay, so over here, so L is, so all of these lengths are like, yeah, L would be, B would be the length of L. AB would have length L plus delta. This would be, so yeah, let me write it out. So L plus delta, L plus delta, written it on top. Okay, and then if I subtract this, I get the second derivative with respect to L. There's yet one more way that I can start with my one interval on the line in the vacuum of CFT and turn a dial. So far, the dials I've turned are making the theory massive, putting it on a circle, putting it at finite temperature. Another thing I can do, another dial I can turn, is instead of having one interval, having two intervals. Okay? Oh, let me just mention one thing, actually, sorry. Yeah. Yeah.
Known if I have a chemical potential rather than a temperature?
Well,
In any ways, it's sort of similar. I mean, in a way.
yeah. So certainly if you have a chemical potential for translations, then it becomes like on a circle, you know, then it becomes a partition function on some tilted torus kind of thing. If it's a chemical potential for some internal degree of freedom, I'm not sure, but yeah, I guess, I mean, I think it's the kind of thing that one could calculate and that has been calculated. But so basically, I mean, I think you'll get a reasonably uniform, universal result because, again, you're on a sphere. Okay. Basically, the important thing to know about CFTs is that sphere partition functions are universal in CFTs. You really don't need to know anything about the CFT except the central charge to know the sphere partition function. And adding a chemical potential, you're still going to be on a sphere, but now you'll have inserted some operators at plus or minus spatial infinity, but you're still on a sphere with insertion of some operators. So of course, it'll depend on the operators. It won't be completely universal anymore, but it's probably quite calculable. Yes? Yeah. That's right. Yeah. So that's the case I said at first where it's a chemical potential for momentum. Yeah. Yeah, I suspect that there's some relatively simple formula that just depends on, you know, some basic data about the thing you're adding. Yes.
there actually they show that what happens is that the dynamic conformal dimension by the square of the chemical potential, and in the end the result is very similar product.
Right.
That one plus mu square and same.
Mm.
So that is more or less what happens.
Yeah, thank you. Okay, I realize there are two things I want to say before I go to the two intervals. So delete from your memory what I was saying about two intervals. We'll come back to that. The first thing I wanted to say is, well, you could say, okay, great, we've done CFT on a line and we've done CFT on a circle, so let's do a CFT on a circle at finite temperature. And certainly you can do that. But what happens then is that now, so when we were doing CFT on a line at finite temperature, it was an infinite cylinder. When it was a CFT on a circle at 0 temperature, it was an infinite cylinder. But when it's a CFT on a circle at finite temperature, now it's a torus. So I do an identification this way and this way. And now, so a priori, that's not a big problem. You can compute torus partition functions in CFT. However, the torus partition function depends now on more than just your central charge, unlike a sphere partition function. But the situation is actually worse than that, because if I start gluing, so now what I've done is I've glued a torus to another torus to another torus. So now I actually get something whose, a Riemann surface whose genus is equal to the number of tori I've glued together. And so now you're doing a CFT partition function on a genus G surface, where G is actually equal to alpha, the Renyi parameter. And that is, first of all, very hard to compute in general, and even harder to analytically continue. And so basically, it is not something that you can compute explicitly, except I think the only case is the free fermion, where you can actually compute this explicitly. But otherwise, it's just, even a free boson, even a free massless boson, which you would think, hey, that's a really simple theory. You really cannot, you can compute those Renyi entropies, but you cannot analytically continue them, as far as anyone knows how to do. Okay? Yeah. Well, for the free fermion, I mean, that theory is simple enough that it has very simple partition functions, genus G partition functions. And yeah, so I believe that for that theory, it's actually been calculated. I don't remember the answer. But anything other than that theory just has the partition functions are too complicated, basically. So as an aside, so okay, that was one thing I wanted to say about this set of things. Another thing I wanted to say is, so this reasoning, again, applies whenever you have a spatially uniform state. So here I've made the implicit assumption that the entropy is just a function of L, that it doesn't depend on the positions of the endpoints, it just depends on the size of the interval. Okay? So in this, I have not said it's a quantum field theory. I've certainly not said it's a relativistic quantum field theory. You're always going to get this thing as long as you have a spatially uniform system. However, if it's a relativistic quantum field theory, then we can say more. And there, we can start moving the interval. So far, everything has been done on a constant time. Okay? on just the t equals 0 slice. But if it's a relativistic field theory, then I can start moving my intervals up and down in time. And if it's relativistic, then I know that for a single interval, it's going to be a function of the proper length of that interval. Okay? And I can use that to my advantage because now I can start considering configurations where things are not on the simple t equals 0 slice. And in particular, so in any 2D relativistic QFT, you can consider a configuration like this, which is like this, but now I'm going to make A and C actually null. You might say, why on earth would you do that? Well, first of all, I'm allowed to do it because in this thing, I'm never evaluating the entropy of A or of C. AB is a space-like interval, BC is a space-like interval, and ABC is. So I'm allowed to make them null. And then when I make them null, now my entropy is a function of this space-like interval, this one, and this one. And what you can show, and this is a good exercise, is that SSA applied to this configuration implies that the derivative with respect to L, the second derivative with respect to L, now of the log, the second derivative with respect to log L of S of L is negative. So the second logarithmic, here is just the second derivative is negative. Now the second derivative with respect to the log of L is negative. These are different statements, by the way. I mean, if it was a first derivative, they would be the same since log is monotone function. But since it's not a linear function, the second derivative, it's a different statement, okay? And this implies that d by d log L S of L for large L is less than d by d log L for small l. And this is a C theorem. Because what is d by d log L at my UV fixed point? It's just C over 3. Okay? Because remember, it was C over 3 log L. And then my IR, if I have an IR fixed point, my theory has an IR fixed point, the dependence on L in the infrared will again be log L, but with the coefficient which is the IR value of the C function. So this implies that CUV, CIR is less than or equal to CUV. Okay? So this is Cassini-Huerta's C theorem derived from entanglement entropies. Okay? Yes? Oh, two.
Yeah, so in this particular case you are taking the entanglement entropy of ABC, is it equal to just B?
No, here you mean?
Yes, yes.
No, it's equal to the entanglement entropy of this interval, which is larger than B.
But isn't the algebra going to be the same for ABC and like just...
Oh, I see, yeah. No, because, I think I need a bigger drawing. So let me put it over here to avoid cluttering. So here I have, this is ABC, and this is its causal diamond. And here's B, and its causal diamond. You see, they're not the same. So this algebra is part of this algebra, but it's not the same. So they don't have the same entropy. It's my fault because I'm moving around too much. Can I just can I just draw this bigger? So, did it move? Okay. At large L and small l. So compared to what? If you have an RG flow connecting two fixed points, there'll be some mass parameter that defines the scale at which the RG flow takes place. So L much smaller than that scale and L much larger than that scale.
I have this more elementary question actually. So, if you start out defining the entanglement entropy in terms of the density matrix, then we have in terms of a wave function, some space-like surface. Now you have drawn some null lines. How do you explain it in a basic way, these formulas?
Well, remember that in a relativistic quantum field theory, what you're really looking at is not a spatial region, but the causal domain of a spatial region, right? And so the entropy is really a function of that, okay? And so this ABC has a causal domain which is equal to the causal domain of just this straight line. So if you don't like the fact that these are null, don't worry about it, just look at this straight line, okay? And that has a certain causal domain, which I drew here. And then AB has a different causal domain, which actually on this thing would be some diamond. And BC has a different one. So they all have different causal domains, okay? And the entropy in each case is a function of them, and the entropies will obey SSA.
How would this log thing come into the picture? You're differentiating with respect to log L, right? How can we see that easily?
That's an exercise. So the exercise for the reader is to show that SSA implies this inequality. And basically, it's an exercise in calculating these proper lengths, because the entropy is a function of the proper length. And the proper lengths, it turns out that the four relevant proper lengths of B, ABC, AB, and BC, thanks to the fact that A and C are null, they obey a certain relation, which basically is easiest to express in terms of the logs of their lengths. So then you write things in terms of the logs of their lengths, and then you should get this inequality. Yeah. Okay, that is a great question. Yes, you should. And so I think, right, so there's like a very, very, very subtle issue here that in my mind has not actually been completely cleared up. So here I've implicitly assumed that that the entropy is relativistically invariant. It's a function only of the proper length. But of course, these are cutoff entropies. And so there's a question of whether the cutoff entropy is relativistically invariant, or whether you can have a cutoff which is Lorentz invariant. And basically, there are good reasons to believe actually that there doesn't exist a cutoff invariant, a Lorentz invariant cutoff for quantum field theories. However, I believe, and Nima or somebody who knows more about this can correct me if I'm wrong, but I believe basically you can rewrite all of this stuff in terms of entropy differences that are actually cutoff independent. So the entropies themselves are cutoff dependent, but somebody who does algebraic quantum field theory, like we've been hearing from Tom Faulkner, that stuff, the entropies in that setting, you're really not computing entropies, you're computing entropy differences, and those things are cutoff independent and relativistic. So I think you can rewrite this in that language, and then it's kosher. Yeah. But it's actually a very interesting question, I think. Okay. So now, the last, yes. Okay, great. That's exciting. I don't know why it would be still open after all these years. Okay, so that's another problem for the reader. A slightly harder. The first one I gave you was easy. This one is harder, is to fix that proof up. Okay, so now the last dial is 2 intervals, and we leave all the other dials at their original setting. So in a CFT on R at t equals 0. Okay? And so now we have 2 intervals here. And now it's just an infinite plane. So it's not a cylinder or anything like that. But you see now, actually, when you glue 2 spheres together, not along one disk. So here, what we've done topologically is just removed a disk and removed another disk, and then we've glued it to another copy. Let's say I just have 2 copies for now. Okay? So now I have a sphere with 2 disks removed and another sphere with 2 disks removed, and I glue them together. That gives me a torus. Okay? And every time I add another sheet, I'm adding another handle to my torus. And so that means that we're in this situation. It's the same difficulty, actually, as at a single interval, but at finite temperature on a circle. Okay? And that means, actually, that there's no CFTs where the entropy of the union of 2 intervals has been computed explicitly, except for a free fermion. Okay? What has been computed with a lot of work for the free boson is the Renyi entropy. So this is one of those cases where the Renyi entropy is known for every alpha, for alpha equals 2, 3, 4, et cetera, explicitly in closed form, and no one knows how to do the analytic continuation. Okay? And that has been an open problem for almost 20 years. And I've talked to countless mathematicians about it. If you know anything about theta functions, it has to do with these what are called Riemann-Siegel theta functions, which are, I mean, a lot is known about them. Mathematicians love them and so on. But this is a function that is, it has to do with obviously some high genus Riemann surface. And if you ask a mathematician to analytically continue in the genus, right, which is what we're doing, right? So here, what we want is a genus alpha partition function. If you ask a mathematician to make the genus of the Riemann surface a complex variable, they go pale, okay? They've never thought of that, which is surprising to me because they love to generalize in all kinds of abstract directions, but somehow this one has not been done. Okay, so this is still unknown. Okay, so this is hard. But we have the answer for the free fermion, And by the way, the answer for the free fermion was computed by Cassini and Huerta in a remarkable way. This is the only case I know of where somebody has actually computed an entanglement entropy this way. You're not going to believe it when I tell you. They wrote down rho sub A, they literally diagonalized it and computed trace rho log rho. It's the only time anyone has ever even attempted to do that in a field theory outside of numerical calculations. Okay, so they have an explicit expression in a field basis for the reduced density matrix, and then they just went ahead and they diagonalized it. And it's kind of complicated, but it's doable if you're as smart as they are. And in that case, what do we find? So let me now call my intervals A and B. And you see that there's like a ton of interesting physics in this. So now we know that you're going to have a divergent part, which is going to be 2c over 3 log 1 over epsilon. Okay? And, with this, we're very sophisticated consumers of entanglement entropy now, and so this is very boring to us. So we're not interested in this anymore. The thing that I spent a whole lecture on yesterday is now boring to us. So we want to get rid of that. And in fact, we know that there's going to be a contribution to the entanglement entropy of, so this is a divergent part, I should have said, of S of A union B. Part of it is just going to be whatever entropy A has and whatever entropy B has. So what's more interesting is to compute the mutual information, which I'll remind you is this. Okay. And this thing has a lot of nice properties. So in particular, this thing is UV finite, because I've removed the divergences associated with the 4 endpoints. The fact that it's UV finite means, so it doesn't depend on epsilon. So in fact, it's not just UV finite, but I should have said it this way, it's independent of epsilon. That's a stronger statement. And that implies that it's conformally invariant. Because the only thing that was breaking conformal invariance for us was the presence of this annoying epsilon, right? You could have said, like, for one interval in a CFT, how can the entanglement entropy possibly depend on the length of that interval? That's not a conformal invariant. And the answer, the reason it could is that there's an epsilon. Okay, so the UV divergence was spoiling our conformal invariance, but once we've subtracted it off, we have something conformally invariant again. And that means that it's a function just of the cross ratio. And the cross ratio, so the cross ratio of the 4 endpoints is a conformal invariant, which is something like, so if I call this separation delta, here I have LA and LB, so you have a cross ratio which is something like this. So in other words, I can look at some other configuration with different values of LA, delta, and LB, and if this ratio is the same for the two configurations, I'll have the same mutual information. Okay? And then we know a lot about this mutual information on general principle. So we know that it, for example, we know that it's non-negative because mutual information is always non-negative. We know. But we actually know more than that, because we can ask ourselves the question, could it possibly be 0 in some theory? And if it was 0 in a theory, that would mean that the reduced density matrix on AB, on A union B, would factorize. And if it factorized, that would mean that there's no correlation functions. So if you take any operator in A and any operator in B, the correlation function would be 0. And that's not true in any CFT, okay? For every CFT, you have at least the stress tensor, and the stress tensor correlation function is definitely not 0. Two-point function is definitely not 0 in the vacuum or any state, okay? So we can actually make a stronger statement that it's positive, okay? We know that by SSA that actually, so this, if I now, so let's just fix, so because of this, I can fix without loss of generality, let's say LA and LB to be 1. Okay, then it's just a function of delta, okay? And then you might suspect that if delta is very large, the correlations should die off. And in fact, you can show that that's the case, that as a function of delta, at large delta, it dies off. In fact, with a power law, delta to the minus 2 h naught, where this is the scaling dimension of the lowest non-identity primary in the theory. You might also suspect that if delta is very small, then the mutual information becomes large. Now there's a lot of correlation between A and B. And you can show that that's true in general, and it's certainly true in the free fermion. So many of these things, I should have said, while it's hard, what you can do is you can actually compute it in certain limits. So in a general CFT, you can compute it at large delta, at small delta, and things like that, okay? And so you see it's coming down from infinity, and it'll look like this in any CFT. In particular, it'll be decreasing. So it's a decreasing function of delta. And the reason is SSA again. But now the SSA that we would consider is the following, that I'm going to add on a C. And now I'm comparing, so this thing, SSA can be rewritten as I of A, B, C is greater than or equal to I of A, B. And so for fixed LA and delta, it's an increasing function of LB. And then when you think about this for a while, you realize that that means for fixed LA and LB, it's a decreasing function of delta. The specific form of this curve will depend on all the details of your theory. Okay, so this is not a universal curve. It doesn't depend only on the central charge. You can have two theories with the same central charge that will have different curves, but they will have this property that it goes to, that it's decreasing, it's ever positive, it goes to 0 with this power, and it goes to infinity here. This infinity is actually a logarithmic infinity. Yes? Well, yeah, so at least morally, I mean, the correlators are, there's a bound relating correlation functions to mutual information, which basically looks like this. So at least if it's a bounded operator, you have something like this. In units of the operator norm. And this is probably stupid, but I'm going to go out on a limb and put the factor of 2. Stupid because it's probably wrong, but that's what I remember. Anyway, this thing you see is all normalized, so it doesn't depend on the details of how I normalize OA and OB, right? Okay, so we know that when this is 0, this has to be 0, but also when this is small, these have to be small. And you would expect it to be saturated by the, if you find the operators with the largest value of the left-hand side, they might saturate this inequality for small values of I of AB. In general, if I of AB is large, if we're in this regime, this is not going to be saturated by any observable because the left-hand side is no more than 1 or a quarter or something like that, and the right-hand side could be 1,000,000. But if you're in a regime where things are like almost decorrelated, which is the case when A and B are very far apart, then you might expect that if you find the operator that has the most correlation still in that almost uncorrelated state, it's going to saturate this inequality, at least parametrically, and that's what happens. And so if you just choose for OA and OB, of course the local operators in CFT are not bounded, so you have to muck around with that a little bit to turn them into bounded operators, but you can see parametrically that this is going to do what I said it's going to do. So that's the kind of moral reason why you have this. It's basically whatever the remaining correlation function is, the last diehard correlation function that's dying off the slowest is going to control the mutual information. So that's the kind of moral reason for this die-off. So in a field theory with local degrees of freedom, that'll never happen. At least if you are, if you have two regions that are on the same space, right, that are part of the same space, then the mutual information can't be strictly 0. There are these topological field theories where indeed the mutual information is 0, but for regions that are not touching each other. But in some sense, you can think of those as IR limits of massive theories. And so if you want to think of it that way, which is the way a condensed matter physicist would think about them, then there's still some residual but tiny exponentially small mutual information. I mean, one thing I didn't say, if you ask, well, what if I make it not a CFT but a massive theory, then again, it'll be non-zero. The plot will actually look qualitatively like this, but at large separation, I mean, first of all, it won't be a function, it won't be conformally invariant, it won't be a function of the cross ratio, but at large separation, the die-off is going to be exponential. Okay, it's not going to be power law anymore. So that's also been computed, for example, in a free massive boson, sort of parametrically. Yeah, that's a massive theory. I would consider that as a massive theory. Yeah.
In general, to calculate partition functions where you have these two intervals, it's hard to calculate, right?
Yeah.
But we know for fermionic, when we have fermions. So is there some way of like bosonizing this partition function so that we can get some bosonic partition function also from this fermionic thing?
Yes. So there is a specific, so when you talk about a free massless boson in 2 dimensions, you should really talk about a periodic boson. And so then the scalar field has a certain periodicity. And it's a different theory if you have different periodicities. And there's only one particular periodicity where you can bosonize it, and it's equivalent to the free fermion. So yes, at that periodicity, we can compute this. But at a general periodicity, we can't.
Partition function for us or not?
Wait, say that again?
So we do have a bosonic partition function.
Yes, I mean, for that one particular theory, which is secretly equivalent to a fermion, we do know the answer. Yes. What's the time situation? I'm out of time. Okay. I didn't hear the buzzer. Okay, the buzzer just went off. So basically, let me just tell you what I didn't tell you, and you can read about it in my notes or many other places, obviously. Where I was going with this which I mentioned at the very start of my first lecture, was how all of the physics here. So first of all, the physics is really visible in every one of these calculations. And then what happens in AdS CFT is that it turns into a geometrical calculation of a minimal surface area. And the physics is always reflected in that minimal surface area. Okay, and so you get the physics of the massive theory, of the interval on a circle, finite temperature, two intervals. All of these cases turn into very simple calculations in AdS, which you can do in a few lines actually in each of these simple cases. And you see how each physical feature is reflected in the geometry, okay, of the minimal surface, or in the language of bit threads, which is equivalent to minimal surface, what the threads are doing. Okay, for that, you'll have to look at my papers on bit threads because it's not in the notes, in the lecture notes. So let me just leave that as an exercise to the reader, basically, if you're interested in this. These are really actually, if you know how AdS CFT works and if you know how the RT formula works, it's actually really, really easy to reproduce every single one of the examples I did today. Okay? Again, with just a few lines of calculation, and to see how the physics emerges in each case and is reflected geometrically. Okay? So that's it. Thank you.
Time for questions.
We've already had a lot of questions.
So maybe Matt, I can.
Oh, well, I'm not sure what you're referring to. I mean, of course, yeah, we could have done this for multiple intervals and it would have gotten more complicated. Yeah.